Hello, everyone. Welcome to today's webinar, Distributed Power Generation from Biomass in North America, Dependable, Profitable Solutions with New Financial Models, sponsored by Turboden. I'm your moderator, Anna Simmet, editor of Biomass Magazine. Before we begin today's discussion, just a few housekeeping items. Questions can be submitted anytime during the webinar. It is helpful if you specify who the question is for. All questions not answered during the Q&A session held following the last presentation will be sent to our speakers so they may follow up on your inquiry after the webinar has ended. A recording of the webinar will be available within a day or two on biomassmagazine.com under the Events tab. 2 polling questions will be introduced during the webinar. We appreciate your prompt replies. Without further ado, I would like to introduce our first speaker, Ilaria Peretti of Turboden. Welcome, Ilaria.
Hello, everybody. Thank you for this opportunity. Thank you for everybody that is listening today. I manage the North American market for biomass and waste-to-energy application. And today I will cover what is highlighted in red in this slide. Next, please. Turboden is an Italian firm and a global leader in the design, manufacture, and maintenance of Organic Rankine Cycle, ORC. They are highly suitable for distributed generation. The ORC can generate electric and thermal power. And they can use different kind of renewable sources like biomass, geothermal, solar energy, and they can recover the heat from industrial process, waste incinerator, engine, or gas turbine. The steam and power, the one in blue, the one in blue you can see there, is a new technical solution for the cogeneration of high temperature heat and electricity with a very high overall efficiency. It is usually employed in manufacturing and industrial processes. Worldwide, Turboden has got 371 plants with a total capacity of 604 megawatt of electricity. More than 80% of them are biomass-based, with a total capacity of 400 megawatt electrical. Next, please. In 1976, there was the first prototype that was using concentrated solar power as energy sources. It was in Perth, Australia. In 1980, the company was founded in Milan by Mario Gaia, professor of energy at the Politecnico di Milano, and today honorary chairman of Turboden. In 1998, there was the first commercial biomass plant in Bier, Switzerland. In 2008, we celebrated 100 biomass plants delivered. In 2013, Turboden became part of Mitsubishi Heavy Industry Group that strongly supports Turboden in the development of innovative solutions. Today, we have more than 370 ORC plants in the world, and we are board member of the Bioenergy Europe. We have thousands of gigawatt hour of energy generated, and the average availability is more than 98%. Cumulative operation time is 13 million hours. Next slide, please. This is a typical biomass configuration plant. You can see on the left side the silo of the fuel. Little bit on the right, you can see a combustion chamber, usually with the movable step grate. there is the combustion of the biomass that usually happens around 900 Celsius, 2000 Fahrenheit. And then there is the heat exchange between the flue gas of this combustion and the heat transfer fluid that could be thermal oil, typically in a biomass ORC configuration. Then there is a closed loop of this heat transfer fluid that brings the heat to the ORC. The ORC produces electricity to be used at the site or to be sold to the electrical grid, and heat, so thermal power generated for district heating purposes, for heat for the drying chamber in a sawmill, heat for a belt dryer for pellet plant, for greenhouses, or the heat can be dissipated through air-cooled condenser or water-cooled condenser. The heat transfer fluid, the heat from the biomass combustion, is transferred to the ORC working fluid by means of this intermediate circuit. This media can be thermal oil, but also can be saturated steam, pressurized water, or directly to the ORC working fluid. Next, please. Key points Turboden ORC technology. It's an easy technology because it's got simple technical feature like low pressure involved, low speed turbine, low number of stages of the turbine, lubricating fluid, no water required. It is unmanned operation or minimal maintenance activities involved, no major overhaul. So usually no qualified operator is needed, depending from the regulation locally, but we have seen so far in North America that no qualified operator was needed in different kind of provinces in Canada and different states in US. The turbine is not subject to erosion and corrosion. There is fast startup and stop procedure, low refill of the working fluid, no chemical and water treatments involved. The ORC, our ORC, is flexible, so you can use different kind of primary energy sources that we discussed before. It is perfect for island mode operation, so for remote community, for example. Its high availability, higher than 98%, and long life. We have seen more than 20 years. It's sustainable, number 3, went from the 4 to number 3. Clean generation of power and heat, reduction of CO2 emission. Next, please. The Turboden biomass solution can be power only, typical electrical efficiency up to 30%, or can be combined heat and power, or combined cooling heat and power, with an electrical efficiency up to 22%. In this case, you want to valorize a lot your heating output that would be at kind of high grade, high temperature. Range size goes from 500 kilowatt to 20 megawatt electrical per single shaft turbine. Next, please. Different kind of fuels can be used. as biomass fuels. Could be the residues from the sawmill, could be bark, wood chip, sawdust, pellet, could be recycled wood waste, like we have many applications in UK. Could be the pruning and trimmings from olive trees, barley dust, rice husk for a rice producer, could be corn cobs, coconut shell, cotton stalks. And you can find different kind of heat user for the biomass application when an ORC is employed. And this heat user would need different kind of heat at different temperature. I mean, so for example, we are going from the low heat user temperature, like the greenhouse, 50 Celsius, around 100 Fahrenheit, using water, district heating that requires usually around 90 Celsius, so 200 Fahrenheit, could be drying chamber for a sawmill, or a combined cooling and power. So the heat out from the ORC condenser would be used to feed an absorption chiller. Could require 110 Celsius, 120 Celsius, so around 250 Fahrenheit, and even higher temperature could be used. That maybe the MDF panel board requires, and the pulp and paper would require around 200 Celsius. Same temperature would be required in a dairy and vegetable oil refining. So 200 Celsius, we are around 420 Fahrenheit. That is steam, in the forms of steam. Next, please. Why choose Turboden for your biomass plant? Because you want to generate profit. That is number one, I believe, valorizing heat and power. Because you want to provide a reliable source of power, also for island mode operation, remote community, or location that have some kind of grid connection problems, issues. You want to use a complete containerized solution that is easy to install with low or zero cost of installation. Do you want to improve the company sustainability also in a remote location? Reducing the CO2 emissions. Next, please. Here we have a polling question. So for which electrical power range would you consider ORC instead of steam? Thank you. I just concluded my presentation, my piece of the presentation.
Thank you, Ilaria, for that nice overview of Turboden ORCs and its applications. Our next speaker is Mr. Alan Fitzpatrick from Equinox Consulting. Welcome, Alan.
Welcome. Thanks. And you can hear me okay?
Sound great.
Okay. So first of all, I'm really pleased to talk about what turned out to be my favorite project in over 25 years in the forest industry, the ORC project. Next slide, please. So I'll just give a very brief summary of the project. I'll talk about 3 challenges that we had to resolve, and the results will actually speak for themselves. Next slide, please. So here's a schematic of the project. In general, the project involved the capture of waste heat from an existing biomass-fired combustor to generate electricity from the ORC. In this diagram, the heat diverted from the cooling tower increased the temperature of thermal oil already used to provide heat to several dry kilns. Next slide, please. This is a picture of the combustor. The combustor is a 25 megawatt step grate system fired with bark. And 2 heaters with thermal oil at 280 degrees and 260 degrees are used. An additional loop of oil was fed into the new ORC building. Next slide, please. And we installed the 2.2 megawatt CHP model. Seen here are the preheater and the evaporator. The closed loop silicone-based operating fluid is circulated using pumps in the basement. The fluid passes first through the regenerator, then to the preheater and evaporator shown here, where a series of coils circulating 280 degree thermal oil converts it to vapor. Next slide, please. This is a picture of the regenerator. The vapor passes through the turbine at the left, then into the regenerator where coils of coolant return the vapor to a liquid and return it to the basement to continue the cycle. A generator is coupled to the turbine just out of picture to the left. Next page, next slide, please. So some of the challenges that we encountered, and every project has challenges, but while we're completing the project, we encountered technical issues in the cooling system and the thermal oil connections, none of which were designed or installed by Turboden. We developed a new on-site technical team to resolve the issues. All the components designed by Turboden and installed performed flawlessly. The new team was really put to the test during startup due to significant changes to the safety regulatory system in BC, administered by the BC Safety Authority. Their entire project approval procedures were completely revamped 2 weeks before our startup date, mainly as a response to 2 devastating dust-related explosions in sawmills in BC. We were asked to provide a detailed analysis of all potential hazards, complete with the safety systems to address them, before they would approve startup. It looked like a very significant delay to our schedule. And at this point, I'll mention the 3rd challenge that we encountered. We had a significant upgrade to the manufacturing facility going online within 3 weeks. We needed power from the ORC to operate it, so we did not have any time to spare. So we turned to Turboden, who provided us with safety documentation to the levels required in Germany. In fact, much higher specifications than those required in BC, which is probably one of the tougher areas in Canada. By working through their concerns with Turboden documents and 2 very stressful weeks, we were able to obtain the reluctant startup approval. Next slide, please. After startup, we completed the first safety management plan in BC. This slide shows a general summary of the safety features within the ORC system. The SMP outlines a series of operating procedures, electrical and mechanical controls designed to prevent, reduce, or mitigate safety issues from identified hazards. Having the plan approved allowed us to operate the plant safely without the need for 24/7 supervision by a third-class engineer, which is the default operating condition in British Columbia at the time. The reduced staffing, operating safety, and scalability of the ORC make it a perfect solution in a remote setting. Next slide, please. And I clearly remember, in fact, I don't think I'll ever forget the project startup day. With the new manufacturing addition ready to test and the BC Safety Authority nervously watching on site, we made the first scheduled start. We discovered one small issue with the guard and restarted. We anxiously watched as the generation level approached our minimum target, then average target, then ideal target, and keep going. We celebrated for all of 15 minutes and then headed off to the new line to start data. As I said, the results speak for themselves. We were fortunate enough to be awarded several awards in the province for the project, and I was very happy to work with Turboden. Next slide, please. Thank you.
Thank you, Alan. Again, you may ask a question anytime. If you see the chat box, you may submit one. Moving right along, our next speakers are Emily Hopkins and Jeff Knapp from Natural Resources Canada. Thanks, Emily and Jeff.
Yes, thank you. We're happy to be here. So we work for the Canadian Forest Service. It's a part of Natural Resources Canada, and Jeff and we sit in Ottawa. Next slide, please. So we have 3 programs that we just wanted to touch base on today. We think that they might, we just wanted to bring your attention to. So these are the federal support programs. The first one is Investments in Forest Industry Transformation, also known as the IFIT program. Currently, the application process is closed. We're just working through our 4th call for proposals and funding additional projects. IFIT, since its inception, we have 145 million in funds since 2010, and this is to commercialize first-in-kind technology. So trying to fund innovative projects in Canada. We just wanted to outline one of our project successes, which was in 2013, which was an ORC system from Turboden installed at the Nechako lumber company. So this was successfully installed, an ORC system here at this lumber mill, and then we'll talk about on the next slide and later in our presentation just about some of the challenges. And then the next 2 programs Jeff can address.
Thanks, Emily. These 2 programs are noteworthy in that they could support the installation of an organic Rankine cycle system as part of what they support. The Indigenous Forestry Initiative, or the IFI program, is still open for applications and is sort of an annual program. They receive about $10 million they have $10 million to disseminate over the next 3 years. That started in 2017 for something that focuses, basically their focus is on forest-based economic development, which means something that's going to provide, ostensibly we're looking to provide jobs and economic development in very remote communities. So what was mentioned earlier by Ilaria, that these systems can be used in remote communities, would be an asset. So the second program is called Clean Energy for Rural and Remote Communities. Colloquially known as the CIRC program, and which is something that is eligible for that is anything that uses biomass combustion. So the process for application is currently open with that program as well. It's a $220 million program that's spread out from April 2018 until March 31st, 2024, and $55 million of that is earmarked for something that uses bioheat or forest-based biomass to produce heat in a remote or rural community. Next slide, please. The goals of the program, of the 2 programs, are very similar. Is environmental, first of all, environmental protection. If there is diesel in a community, there's the potential for spills and for air pollution, obviously. We'd like to reduce greenhouse gas emissions, one of the main priorities of the Canadian federal government right now. And we're looking to do some economic development in remote areas that don't typically have that much going on economically. We're looking to build the capacity in those smaller communities so that they can do big projects like this and that they could manage a system like an ORC system or solar or biomass combustion, geothermal, any of these things. We're looking to encourage energy independence in these small communities so they're not depending on large oil companies, and give the community back some control of their resources, like their forest resources. And ultimately, one of the government's main priorities at this point is reconciliation with Indigenous peoples. Next slide, please. So when we run projects through, somebody suggests a project and they send it in to us, we give it to an expert review panel that's typically made of experts outside of Natural Resources Canada, recognized experts from Canada, and they come up with these questions. So in terms of an ORC technology, some of the questions that they have, I've listed here on the left-hand side in terms of risks and challenges. And it would be helpful if when the Turboden folks, and they've already spoken to a couple of them, but if they can speak to some of these things, that'll be very helpful. Quality and the consistency of feedstock. Does it require a particular type of feedstock? And they've already indicated they can run on bark and sawdust and a bunch of different things. What quality of feedstock does it need? The maintenance, does it require a highly skilled person, a highly qualified person? They've already mentioned that the qualifications aren't that high, but what about the logistics of maintenance of it? Can a remote community manage the manpower to do that? The availability of parts. Can you get parts for these things in Canada? These are questions that the experts had. The operation, do you need to educate the people that are going to be operating it very carefully? Regulatory compliance in each province. Does every province allow an organic Rankine cycle system to be put in? And will it operate in remote climates at -40? How reliable is it? And is the technology viable in the Canadian climate? Emily?
So just some of our lessons learned from that IFIT project at the Nechako Lumber Company, where we installed successfully that ORC system. Some of the setbacks we had to overcome was really understanding and meeting all of the requirements of major stakeholders and regulatory authorities. So there were 8 major stakeholders for that project. They ranged from like provincial government, workplace safety organizations, utilities, and onwards. So just understanding all of their requirements to make sure that your project can come in on time and on budget. And then typical project delays. I mean, this is going to be typical of a first-in-kind technology with new people putting the project together, just making sure that everyone is aware that this, you might have some delays and you have to overcome them in terms of the piping and installing the ORC system. Next slide, please. So this slide is really just to leave you with contacts, so initial points of contacts within the federal government. If you're looking for federal funding, the Clean Growth Hub, which is sort of like a concierge service, it's you can go to this website and talk to them. They'll be able to look at your project and direct you to which federal funding programs might be suitable for your project. On the right-hand side is the Innovation Canada. It's a digital platform, so it's on the web. You sort of walk yourself through the questions on their website, and then they'll sort of spit out a tailored list of different federal government programs available for your business. It might not include all of the programs, but it will give you a good indication of where to start.
And just as a last point, we've had in the bioheat component of the Clean Energy for Rural and Remote Communities program, lots of folks have applied to install organic Rankine cycle systems in remote communities. So it's really important for us at this stage to know whether or not it's a viable technology in Canada. We would love to support this, and we would love to be convinced that it's viable and we can encourage these people to adopt them.
And then that concludes our presentation. So thank you very much for having us.
Thank you, Emily and Jeff. Moving right along, our next speaker is Terence Saw from the Ontario Ministry of Agriculture, Food and Rural Affairs. Welcome, Terence.
Hi, can everybody hear me well?
Yes.
Okay, thank you. You can move on to the next slide. So I'll briefly talk in a couple of minutes. The different priorities for the farms and the food processors. I can't touch on all the different food processors out there and all the different farms, including the greenhouses. As Illyria identified, the greenhouses can use much lower temperature heat and are a good candidate for ORC technologies. Next slide, please. So the main priority of the food processor, if you want to deal with them, is that their first goal is to comply with food safety regulations and making sure they do not produce bad food. So if you do have a project in mind for these type of clients, or you are this type of client, you have to always keep in mind that this is your main business. And typically, these type of clients always adapt or change their behavior based on if there's any incentives present to be more cost effective, or if there's some science available showing or indicating them that they can comply with their priorities, or reducing the risk of foodborne illnesses. The smaller farms and smaller food scale processors, we've been lucky with the feed-in tariff program in Ontario. Actually, quite a lot have included small trackers for photovoltaics, or on just normal base. Some significantly large solar farms are also put up. But we've also been lucky. We have experience with combined heat and power plants that are using biogas as a fuel. We probably have around 47 now running on the grid and producing electricity and using the heat on site. So these sites go from about 200 kilowatts electric to 1 megawatts electric. And in terms, I know some people talk about, is there any biomass or agricultural residues out there? Yes, there are, but there's a market for them. So there's a significant value for these products. And right now, if you want to use them for energy, there's no economic return or economic incentive right now. Next slide, please. So the way you want to discuss with a food processor if they would be willing to use any form of biomass heat or biomass energy is they respond through consumer demands. So me, if I go to Walmart and I say I want a carbon neutral yogurt, then this may be the way that a milk processing plant may say, well, I have some clients asking for something specific, low water consumption or FSC packaging. That's how the food processor will respond. And also there's a specific sustainability requirement for food processors and farms. If you want to know more about that, you can see the American Society of Agricultural and Biological Engineers standard on that. I don't think there's a new work plan, so that's a pretty stable sustainability plan that's available and set up for anybody to follow. Next slide, please. So there's a couple of things that you have to discuss with the food processor before they want a biomass CHP or just a natural gas CHP. Is that what are your clients asking? So people that eat your food and buy your corn, do they want specific information from you? So like I said, packaging material, is it in plastic? Is it in paper? Is the paper FSC certified? What's your carbon footprint? Where do you buy your products? Do you deal with any local farmers? And if you're part of a traceability system? So these are the things that are in the mind of the food processor first. So if you think that it's a good fit, usually the carbon footprint is pretty good because you can displace natural gas or propane being consumed on site. That's a good way to tap in to these clients. But you need to know what are called KPIs, key performance indicators. So sustainability asks that these key performance indicators and how to improve them, because your clients or your supply chain is asking for these key performance indicators. But the best is to actually hire a energy or utility manager and auditor, because the first thing you have to figure out is before producing or investing in renewable energy, you have to know how much you consume, and by knowing how much you consume, you can be more efficient in your process. You can drop the wastage of bread or the wastage of milk or cream that you waste at the plant. You can also save water by improving your sanitary measures, and also you can reduce your sewer surcharges that the municipal wastewater treatment plant charge you because you're sending food down the pipe. So that champion is the person that discusses with the different utility and knows how much energy and how much is coming in and coming out of the plant, and they help providing key performance indicators to the management board. But most and foremost is any energy efficiency project is always should be on the first mind. They have a shorter payback because they don't need capital, or very little capital. Sometimes they can only just need some management changes to be more efficient. So I would typically favor energy efficiency projects before considering a large significant investment, unless there's a strong demand by the consumers to improve the carbon footprint of your products, as an example. Next slide, please. So the greenhouses have a good record and knowledge of using biomass. There's about 17 greenhouses that can, or maybe now 18 actually, that can use solid biofuels. So they mainly use wood residues from either Toronto or other urban areas around southwestern Ontario. They're actually a pretty good candidate for using solid biofuel CHP or any other CHP technology or heating technologies, I mean, because of their energy profiles. So they'll use a lot of the heat during the fall, winter, and spring, and not everybody has that heat demand or energy profile, so that obviously you need to hire that energy auditor and manager to figure this out. And the CHP is always a good idea because there's actually a lot of water storage present in those greenhouses that are using wood as heat. So you can send all the heat from the CHP into that water storage tank and increase your utilization efficiency of the plant. Next slide, please. Yep, and I think I'm done. And if you have any questions, please use the chat, and we'll address them at the end of this webinar. Thank you.
Thank you very much, Terence. Our next speaker today is Natalie Hemeliers of Bioenergy Europe. Welcome, Natalie.
Yes, thank you, Anna, and hello, everybody. So the objective of my presentation will be to give you maybe not an overview, because in 5 minutes it will be very challenging, but some insight in the European market and policies for biomass electricity generation. So next slide, please. So I will start with some information on the European market. So just to let you know as well that all these information, data and statistics come from Bioenergy Europe statistical report that is published every year. And that contains about 200 pages of data and statistics on the European bioenergy market. So if you are interested, don't hesitate to contact me. So on this slide, you can see it's the European electricity mix, where you see basically that we have about 30% of our electricity generation that comes from renewables, and 5% is actually biopower, comes from biomass. So it is still a small share compared to the heat sector, but it's quite still 5% is quite important. So next slide, please. So these 5% are an aggregated, an EU aggregated number. So as you can see in this slide, this amount of this percentage of electricity generation from biomass is varying among EU member states. So as you can see in Denmark, Finland, Latvia, Lithuania are really the countries that produce mostly their electricity from biomass. But then you have other member states that produce, of course, much less. Next slide, please. So it's also interesting to see in what type of installations the biomass electricity is produced. So we see that 58% of the electricity produced from biomass is produced in CHP, while of course 41% is in power only. This really shows that more and more, and this will increase, and I will link that with my very last slide. We expect really an increase of electricity production via CHP. Next slide, please. So here you see the type of fuels that are used in the EU for biopower production. So you see it's mainly 50% is solid biofuels. So this is mainly woody biomass, but also some agricultural biomass. You have also, of course, an important part that is biogas, so electricity production through biogas, and this is mainly agricultural feedstock as well. Same for liquid biofuels, it is mainly agricultural feedstock, and then 12% is organic municipal waste. Next slide, please. Here is an overview also of the job creations in the EU, and as you can see, the bioenergy sector is employing the greatest number of people among the renewable industries. Again, here you see the different sectors where you see that solid biomass is more than 50% of job creation, and then the others are biofuels, biogas, and waste is the other half. Next slide, please. So yeah, I wanted also to give you a quick update on policy, on the policy side, because I thought that it was very important to share with you this new provision that we have in the very recently voted Renewable Energy Directive. This directive will set the legislative framework for renewable energies between 2020 and 2030. So it's quite an important source of legislation for bioenergy, as you can imagine. And there is within this directive new requirements for biopower installations. So as you can see, for installations above 50 megawatts, there will be these requirements, because below 50 megawatts, there is no specific criteria. But between 50 and 100 megawatts, electricity produced from biomass will have to be produced either in a CHP, either in a power-only installation, but with an efficiency level compared to the best available technologies, which is an efficiency level between 32 and 38%. Or it has to be coupled with CCS, with carbon capture and storage. We have the same thing for installation above 100 megawatts. So they have to be produced either in CHP, either with a 30% efficiency level, either coupled with CCS technology. Also, it's important to note that the power-only installation will not be able to use fossil fuels as a main fuel. So this is to prevent co-firing with biomass with about 5 or 10%. Biomass will have to be the main fuel if it's co-fired. So that's also an important new element in the European legislation. And this all these requirements will apply 3 years, to all the plants starting operation 3 years after the adoption of the directive. The adoption of the directive is next month. So that means that starting 2022, the power-only installation in Europe will have to comply with these requirements. So that's really, in a nutshell. There is also another very important new element in the Renewable Energy Directive, that is the new sustainability criteria for solid and gaseous biomass. So we have a whole scheme now that is being developed, and that is really improving the sustainable production of biomass. So this is the new Renewable Energy Directive, and I will conclude here, and I'm happy to take any question if there are. Thank you very much.
Thank you, Natalie. Our next speaker is Mr. Ricardo Vescovo from Turboden. Welcome, Ricardo. You may begin your presentation.
Thank you, Anna. So I will cover in this session these 2 points. So key factors for success in a biomass project, and we'll talk about some biomass reference projects. Next slide, please. So we have seen as technology providers quite many projects in our 30 years history. For the biomass projects, what we see is that there are 3 main factors that have to be addressed to get to a successful project. Actually, there is a 4th factor, but I will talk about that later. So these 3 factors are the fuel. So the fuel must be available as close as possible to the plant at an affordable cost in the long term. It is not. This is quite important because in the long run, also availability of large amount of fuels may disappear because of other new installation that will be born close to the plant. So this is a quite important factor to be addressed. Another important factor is the heat. As also discussed in the previous speeches, the CHP configuration allows the valorization also of the heat generated by the plant. This is not always possible, but when possible, this gives a very good advantage for the success of the project. The power, electric power, is the 3rd important factor, and is especially more important when heat is not valorized in a CHP scheme. So the value of the electrical power generated in grid-connected system is typically low. So in a biomass project, for a successful biomass project, feed-in tariff or renewable incentives in general must be in place. In remote communities, in island mode configurations, there is a natural high value for the electric power generated. Let's say when going through this slide, there is I recognize there is an additional factor which is very important, but from our perspective we don't see it, which is the technology. So next slide, please. A successful biomass project can be achieved if you have a reliable and dependable technology. We are technology providers, so we give this as obvious, but it is not that. So what we see and what our story says is that we can provide a good technology. We have more than 300 plants running only in biomass application in about 30 countries worldwide. Our technology requires very low operation activities and as well as very low maintenance requirement. It's a very automatic system. We as company have access to a very well-established network of suppliers for balance of plant equipment, so we can support customers indicating names and contacts for suppliers of parts not supplied by us. And we can also supply a long-term service agreement up to 20 years maximum to guarantee that the plant performs at high levels for all its life. Next slide, please. We see here a statistic about the 300 and more plants we have in biomass projects. I go through that. About 75 plants are installed in the wood industry, sawmills, MDF, and panel board. These plants are all of them CHP, and this is where the ORC technology was firstly installed. Because here there are all the natural, the three factors, the important factors for this biomass success are there, because there is a biomass available in the long run, there is a user of power that gives a high value of that, and there is the usage of heat for the process. We have few plants in the rice and cereals and food production, quite many also in the district heating, because our technology can be easily integrated either in new or existing district heating networks. We have quite few also for the pellet production and also charcoal production, and about 5% of the plant are employed in power-only cases. Let's say in Europe, which is our main market, in grid-connected projects, the value of electricity is not always as high enough to sustain the economics of a power-only project. Rather, all the rest of the projects are CHP projects. So before jumping to the next slide, I will, or with the next 2 or 3 slides, I will give you the answer to the polling question done earlier by my colleague Ilaria. So what is the right size for the ORC unit? So all the answers provided are correct. So next slide, please. So historically, ORC technology for biomass application started from the low size. So this is a plant which is about 20 years old, and it's a 500 kilowatt electric. It's a CHP unit employed in a sawmill in Austria, generating hot water at 90 C for drying kilns. Next slide, please. And here we go to so this was a 500 kilowatt. Now we show this very important reference installation we have in North America, in Canada, for West Fraser, which is one of the largest lumber production facility in North America. And here we have installed in 2 sites, 2 units per site of 6.5 megawatt each, for a total production of 26 megawatt electric. And as a third case, the next slide, please, we show this other project installed again in the US for Athens Energy, which is in operation since October 2016, so it is 2 years of operation, and this project has a gross production of 8 megawatt, and it's employed as a power-only unit in a wood pellet production facility. So this is the largest single Turboden unit employed in a biomass project. Next, please. So here we have another polling question. Which is the main driver of a biomass project in your opinion? So we take few seconds for you to reply. Okay, so let's go through that. So 73% of the answers are indicating economics, 23% environmental sustainability, and 2% energy efficiency, and other 2% CO2 certificates. It's what I expected. So let's say economics, or the economics is most of the time the driver. And sometimes the environmental sustainability may provide an additional push for a project, even if economics is not the best, but economics is the driver. So I'm done with this part.
All right. Thank you, Ricardo. Our next speaker is Johan Van Toff from Tigoga Development Corporation. Welcome, Johan.
Thank you, Anna. I very much appreciate the opportunity to share. This presentation is going to speak very briefly to the application of the Organic Rankine Cycle in Canada to solve the issues in our remote communities that are several hundred kilometers from either the road or from rail. And we have, frankly, a substantial issue there. Next slide. What we have, particularly in First Nations, most of these communities are First Nations or Indigenous, and we have several hundred communities that are not connected to the grid. They fly in diesel in planes, in the bladder of planes, and the price of electricity depends on the distance they fly, but it's about $1.20 to $1.50 Canadian a kilowatt hour. Anybody who knows diesels know they're old. The maintenance is prohibitive, and there is no budget to replace. And what we see in the Canadian context is the installed capacity per capita in these communities is 1 to 2 kilowatts per capita, whereas in the Canadian context it's 5 kilowatts. They're constantly under capacity constraints. They're told to turn off lights, and many of these machines are way beyond their hours. And so as a consequence, we have a substantial issue. The cost is partially subsidized for residences only. Commercial operations are not very much subsidized. In Ontario, there's $175 million that is tacked on to the ratepayers. There's 4 million ratepayers in Ontario. But the federal government and the First Nations essentially get no subsidy, and they pay 94 cents a kilowatt hour. There are several boil water advisories, and most of them are not replaced because the electricity capacity is not available in the community to run a new plant. So we have a substantial issue, and we've been criticized by the United Nations, rightfully so. Next slide. What we have determined is that the Organic Rankine Cycle really works, and it works on an energy-only basis, not heat. And I'll explain why in a minute. It is a proven off-grid solution. Its ramp-up and ramp-down rates are good enough, together with remedial actions schemes. It aligns with the self-reliance objectives. We're looking at 14 to 22 jobs, depending on the size of the community, and it can be connected to a transmission line if it were ever to come. It's base load, wind and solar are not. It does have load following, and it avoids expensive utility-sized batteries. The prices we're seeing for batteries is 1 megawatt hour is costing $1 million. So the battery solutions are not there yet in terms of competitive. And the cost reduction that we have modeled is, again, on an energy-only basis with no revenues from the heat, is about 65%. So we're looking at about 43 cents a kilowatt hour, and that would include free heat. Next slide. What we are doing as developers is that what kills projects is time, and what produces the time in projects is dependencies. And so if we are dependent, I'll just go to a project that my team did previously, which you can Google. It's the Montana-Alberta transmission line, where we built a line between Alberta and the United States and connected Alberta to the U.S. We sold our transmission rights to 600 megawatts of wind. We couldn't get banked because they weren't built. They couldn't get banked because we weren't built. And so you have project-on-project dependencies, and what that does is to produce 2 years of running around bankers trying to get somebody to take your deal while you're spending a lot of development cash. What we have done is to avoid all the dependencies we possibly can. We've hung on to permitting, but you'll see in a minute our projects are all going to be owned 100% by First Nations, because we don't trust the process with bankers and with equity providers to get to shareholders agreements in anything approaching the kind of schedule that we want. So we are retaining only permitting. The procurement will be all done ahead of time. The financing is all going to be private sector. We have 12 life insurance and pension funds that are prepared to finance these. We have an infrastructure fund that's putting up the funding for the first 5, and because it's going to be 100% community owned, we will be able to avoid those dependencies as well. So this is very much our mantra: is that our permitting timeline is about 12 months. Our construction, together with the Turboden folks, is about 12 months, and so we are 24 months from concept to turning it on. Next slide. So what you see here is the project structure. The community will own 100% of the Energy Co. The power purchase agreement, we have a number of off-grid standing proposals. So in Ontario, there's one called the Reindeer Rate, which has prices for individual communities, and they range from about 35 cents to 71 cents, depending on the distance. So the very northern one, Fort Severn, is very high. The biomass will be sourced locally, and we have the biomass over 50 years for the average community will be equal to 1/2 of an average fire. Up in that part of the world, in the boreal forest, the entire forest burns completely over every 100 years. So this will be the biomass required, depending on the yield and how far north you are. It's about 1/2 of one fire. We will have, obviously, boiler and turbine relationships. We've developed those. Our role is to develop, finance, build, and then we will monitor operation. And we have the development capital that we're putting up to fund the permitting, which gets repaid out of the project finance. Next slide. The project finance is very classic, plain vanilla project finance, the kind of stuff that gets done every day in Toronto and New York, and it therefore reduces the timeline of dependencies. These are financings that get done in 75 days once you have everything ready. We have mezzanine standing by. It'll go in as preference shares. We have senior debt. 10-year, 6.5, might be 6.75 with the interest rates rising. And so on a classic 5 megawatt project, which we think is coming in at 30 million Canadian, the 30 million would be all the EPC, the development fees, interest during construction, deal and legals, debt service reserves, maintenance reserves, owner's agent. In other words, it's the full project cost, and that would then repay our development fee, and then we obviously put that into the next project. So that is the financing structure, and that's why we're not looking to government capital, because that introduces a dependency, which introduces schedule. So that's what we're doing in the community. I'll just relate this to one alternative, which is transmission line. Next slide, please. One of the proposals, the alternative to distributed generation, where you are disintermediating diesel, is transmission lines, and we have a proposal in Ontario which is called the Watay line, and my team and I are very familiar with transmission lines because we built one, and we've had all the construction challenges that you can imagine. In this context, if you look at a 5 megawatt system for a community of about 2,000, that's on the right-hand column. The middle column is Watay. which is the line that is proposed. It's $1.8 billion estimated for an 1,800 kilometer radial line with 17 substations. We think that there are no roads. This is all going to have to be helicopter built. It's going to deliver 24 megawatts to 16 communities, whereas we would deliver 5 to 1 community. And that would be upsized because these communities are all underserviced. The capital cost per megawatt hour delivered is there, 73 to 6.5, and the population served is 16,000 versus 2,000 on the largest community. The cost per resident, 112,000 versus 15. There's no redundancy if the line goes down and you have to fly a helicopter to find out where your insulator's broken, and you're down for days or weeks. Whereas the redundancy here, and you see with the availability, this is why we selected it. Local employment would be de minimis. We would have substantial local employment because we're insourcing the fuel. The time to do this, power lines today are 15 years by the time you've designed and built it, whereas this is 24 months. And then the cost, and this project in the Wate is proposed to have a government grant of $1.3 billion. So we factored in the cost of the $600 million private money together with the O&M. And you see the numbers there, so there really isn't much for say. So what we have found in Canada, to conclude, is if you keep the dependencies down, and even with no heat, we found that this beats diesel by a country mile. So our strategy, to conclude, is we are executing on energy only, with heat use coming in afterwards. Thank you.
Thank you, Johan. And finally, Ricardo is going to wrap up presentations with some conclusions.
Okay, so thank you, Anna. I will, as you said, go through conclusions, but first I will provide some insight of a new product we are developing. So next slide, please. So we have heard today, and we see in the market every day, especially in Canada, but also in other remote communities around the world, the need for a technological solution to allow to boost, let's say, the transition from fossil fuels, diesel oil, to renewable energies. We as Turboden are the leader in electric power from biomass in distributed power generation. So we felt ourselves in a very good position to develop a new solution to address this market need. And we are working on this project, on this technical solution, which is a 1 megawatt plant, especially suitable for remote communities. And what we are proposing is a turnkey solution with the electric power between 500 kilowatt up to 1.5 megawatt electric. Given the distance from the industrial areas, this plant is fully pre-assembled in container skids, so that are easy to transport and for easy installations. So no buildings are required. We have found a very good solution for high efficiency, and this is a totally water-free solution. So it's especially suitable also for places where the temperature goes quite low. So there is no issues of freezing. The system is suitable for island mode operation. It can operate with different fuels. Clearly, it must be designed for a certain fuel, but it can work with wood pellet or wood chips, or also other wood residues. And as it maintains the typical ORC feature of being a totally automatic system with a very low operation and maintenance needed. It's fully automatically basically, and also it it has a very low emissions in terms of pollutions. So this is a system we are developing and that we can provide together with our partners in North America to address these remote communities' needs that we see. Next slide, please. We are at the end of this webinar. So we have touched many points. So we have seen an introduction of ORC Technology and especially Turboden Company, which is the sponsor of this webinar. We have also seen real cases from companies that have installed this technology, but also a very interesting view from policymaker, but also statistics on renewable energy and bioenergy in Europe, and also the opportunities that are there for public fundings, but also for private fundings for this type of projects. So what we see is that we can provide a proven solution for the transition to renewable energy supply in remote communities. We are available to provide any support for you that want to develop this type of project. So thanks for your attention to all the speakers for their participation to this webinar. We will have a short session of question and answers now. We will, in any case, we have recorded all the questions done by the auditors, and we will reply in the next days by email. So next slide, please. And please, Anna, you can move forward with the questions.
Thank you, Ricardo. Again, if you do have a question right now, please submit it. And as Ricardo said, they will follow up with you privately following the webinar. The first question is, what is the typical delivery time from order to startup of a complete biomass plant?
The typical delivery time from order to startup of a complete biomass plant is about 12-14 months.
Thank you. The next question is, how does Turboden take care of after-sales contracts?
So we have a department which is the after-sales department that takes care of all the after-sales activities. So we have about 50 people working there, and about half of them are here in the office for remote monitoring of the fleet, and the other people are going around in the world to make the scheduled and unforeseen activities on the fleet that counts today 300 running plant and almost 400 other 100 units under commissioning. We have also a few partnerships with local companies in some geographical areas where we're not directly present, and also given we have about 10 to 15 units installed in North America, we have a person based in Canada that is serving this market together with local partners.
Thank you. The next question is, what is the cost of investment for a biomass plant of 1 megawatt from the silo of the fuel boiler to the ORC?
The cost of investment for a biomass plant of 1 megawatt is about $8 million US, about 10 million Canadian dollar.
And a follow-up question, what's the cost to operate and maintain a biomass? Oh, I asked that one. Excuse me, what is the cost to operate and maintain a biomass plant of 1 megawatt?
So the operation and maintenance cost of a biomass plant, not accounting as operation cost, the cost for biomass, it's about typically 5% of the investment cost.
Thank you. The next question is, what is the working fluid in the ORC?
The working fluid in the ORC could be silicone oil or hydrocarbon.
Thank you. Our final question is, what is the heat transfer fluid between the boiler and the ORC in a biomass plant?
So very typically, the thermal oil is used as heat transfer fluid. Thermal oil, differently to other fluids, is always in the liquid form, and it's very easy to be controlled. There are thousands of plants in the biomass market using thermal oil as heat transfer fluid, and it allows a very easy operation of the systems, and is also very common practice in the wood industry, especially in the panel board industry.
Thank you. That will conclude our Q&A session. Turboden and our speakers will follow up with all unanswered questions. With that, I would like to thank today's sponsor, Turboden. By joining us for this webinar, you are eligible to take advantage of a 10% discount off a full registration at the International Biomass Conference being held in Savannah, Georgia, March 18th through the 20th. Be sure to check out our other upcoming events. And that will conclude today's discussion. We hope you found value in it. Thanks for joining us and have a great day.
Thank you.